Hey everyone, welcome back to Math 256. This is Scott. Let's get started. So now what we're going to talk about is section 1.5, where we will look at linear first order differential equations. And as always, the differential equations we'll be talking about are ODEs, which means ordinary differential equations, which means no partial derivatives are involved. So linear first order ODEs. So the format that makes it linear as opposed to some other form is this. So this is the format. So linear. So for a linear equation, the format has to be something in this format. So y prime plus p times y is equal to q, where p and q are functions of x. So we have capital P, capital Q, and those represent two functions of x, and the format that we're talking about here is we have a naked y prime, we have something involving x, all times y, and then we have just a q. So what's linear about this is it's linear in y. Okay. An example of a linear differential equation along these lines would be something like dy dx plus 2y is equal to e to the x. So this is an example of just such a thing. So here the roles of p and q will be played by 2 and e to the x. All right. So this is the format, this is an example, and now let's discuss the technique that we're going to use. And this is what's called an integrating factor. Okay, so here's the basic way this works. Look at the example that we've got right here. What we have is a derivative of y. What we have is something times just a y. And then what we have is something else. But the important thing about this is that it bears, if you look at it hard enough, some resemblance to the product rule. And in particular, if you look up here, this is also kind of like the product rule, in that we have a factor times a y, and what we have here is the derivative of just that. And the ultimate goal here is that we want to figure out how to turn this into an instance of the product rule. So the philosophy here, or the strategy, the idea, turn the left side of the equation into the outcome of the product rule. And then use this to solve for y. And the stepping stone that we're going to need in order to go from what we have here to the product rule is going to be the integrating factor, which we'll call rho. So rho. So don't mistake it for a p. It's the Greek letter rho, the equivalent of our letter R. So the rho here, this is going to be the integrating factor. Integrating. That will multiply both sides by to get the product rule. So in other words, we'll take the y prime plus the p y is equal to q, and we'll multiply both sides by rho. So that means it's going to be rho y prime plus rho py is equal to rho q. And in particular, what we want is this to have the form of rho prime. So what we want rho times p to be the same thing as rho prime. And the way to make this happen is as follows. So we can use rho, which is equal to e to the power of the integral of p dx, or actually, dx. So we can use this because then rho prime will equal, according to the chain rule, e to the integral p dx times the derivative of the integral of p dx with respect to x, which in other words is just going to equal e to the integral p dx times just p, which means, in other words, just rho times p. So what we can use is the integrating factor that we get from this. So then we have going back to the original equation, we would have rho y prime plus rho prime y is equal to rho q, which then would mean that what we have here is rho times y all primes, because this now is the product rule. Is equal to rho q, which means that then if we want to get this, we can anti-differentiate both sides and get rho times y is equal to the integral of rho q dx. And then what that means, and then here there's going to be a plus c. And then what that means is that we can then solve this for y by multiplying by rho to the negative 1, or in other words, dividing by rho. And here, the constant of integration that comes up is going to come up right here. And so rho, which is going to be a function, is going to have to get multiplied, or 1 over rho, which is a function, is going to have to get multiplied by that constant of integration as well. So that's going to be a bit of a technicality that we're going to have to keep track of, but we should be all right. And we'll just call that good. So we could return this all the way to its original p's and q's by putting in for rho what it is supposed to equal, but that would not be too helpful. So a note here. In finding rho, which is equal to e to the integral of p dx, we don't have to worry about a plus c, because all we need is any antiderivative of p for the equation to be satisfied. We just need any antiderivative. Doesn't have to be any particular one, so we don't have to hedge our bets with the plus c. But, however, when solving for y, we do need to include plus c prior to multiplication by 1 over rho. So let's now watch this play out. So let's go back to that example. That example we had to motivate the very concept of a linear differential equation. So it's going to be the first in a series. So we have dy dx plus 2y is equal to e to the x. And as we said already, that means that p is going to equal 2. Q is going to equal e to the x, which means then that rho is going to be equal to e to the integral of 2 dx. So is the integral of p dx. And so then that's going to be e to the 2x. So then the whole purpose of this is you multiply everything by e to the 2x, and what you're going to get is actually here, I'm going to make that more explicit. So then rho dy dx plus 2 rho y is equal to rho e to the x. And here then what we're going to end up with is this is the same as the derivative of rho. So this all ends up collapsing down into just the derivative of y, or rho times y. This all collapses down into the derivative of rho times y, and that's equal to e to the 2x e to the x. So now I'm gonna go ahead where it's convenient, and where it's convenient to, I'm gonna go ahead and put in what rho actually is. Rho times y prime e to the 3x. Now, so I'm just combining those. Now I want to take the antiderivative of both sides. So that means that rho times y is equal to the antiderivative of e to the 3x dx, which is going to equal 1/3 e to the 3x plus c. That's still equal to rho times y, which then I divide both sides by rho, and I'm going to get, y is equal to 1 over rho. So in other words, 1 over 2 dx, 1/3 e to the 3x plus c, and then here this is going to distribute, and so what we're going to end up with is going to be 1/3, and it's going to mostly cancel, and we're going to end up with just e to the x plus c divided by e to the 2x, or as we'll rewrite it, 1/3 e to the x plus c e to the negative 2x. So this is now our solution family y. And notice the parameter here is not just a straight up constant of integration, it's a constant of integration times a factor of e to the negative 2x. And it's going to require an initial condition to determine a value for that particular c. All right, let's try this again. So, example B. Now let's take something of this form. 1 plus x squared dy dx minus xy equals x. Now in this case, we are not currently in a position to declare what the p and the q are, because this is not actually currently in the authorized linear form. This should only be dy dx. So in order to make it linear form, we need to divide everything by this in order to get it into standard form. So to get proper format, we divide by 1 plus x squared. So dy dx minus x over 1 plus x squared y equals x over 1 plus x squared. So we needed dy dx alone. That's why we did that. Okay, well now that we have this, we can now make our judgments, and so here we can say that p is equal to negative x over 1 plus x squared, and then that's that's going to mean that rho is equal to e to the power of the integral of negative x over 1 plus x squared dx, which then is going to be the same if we do a little bit of cleanup here, and I can use the alternate notation. For the exponential functions here, whenever the expression up here gets a little bit ungainly, so I can use rho is equal to exp integral. I'm going to bring the negative up. X over 1 plus x squared dx, and this is an occasion for u substitution on account of the fact that the derivative of the denominator is going to be 2x, which is only a constant factor off from what the numerator is. So that gives us a choice of 1 plus x squared for the u, which makes the du 2x dx, which then converts our rho into e to the power of, or exp, negative, and then the integral of, and let's see, so up here that means that x dx, which is what we have, is the same as 1/2 du. So this is going to be the same as 1/2 divided by u du, which is going to be exp negative, and now what we have here is 1/2 natural log of the absolute value of u. And again, we don't have to worry about the plus c on this because here we only needed this to be a single antiderivative of of the p. It doesn't have to be every antiderivative. So now this is going to be the exponential function negative 1/2 ln x squared plus 1. And notice I don't need to worry about the absolute value because this is always positive, so I dropped the absolute value. And that's because x squared plus 1 is always greater than 0 for any real value, and that's all we're talking about right now. So then, thinking about this, what we've actually got here is the same as exp. Now let's think about this. So we've got an exponential function here and a logarithm here. So clearly there's some suspicion that you might have that these are going to somehow cancel each other. But this isn't going to work as long as what we've got is not just a naked logarithm, but a logarithm with extra factors in front. And so the negative and the 1/2, we're going to want to use the laws of logarithm to rewrite that in such a way that the logarithm here is all by itself with the hope of it canceling with the exponential function. So in order to make that happen, we're going to pull the negative 1/2 up into the exponent spot using the properties of logarithms. So that's going to be ln x squared plus 1 to the negative 1/2. And that causes these to cancel each other. And then that gives us, so these are all what rho equals that, rho equals that, rho equals that, rho equals that. This is now our final, most simplified version of what the integrating factor rho is going to end up equaling. And now what we do with this integrating factor of rho is we multiply the entire function by it with the hopes of being able to get ourselves into the outcome of the product rule. Now then, rho y prime minus, sorry, I should say plus rho prime y is equal to rho times x over 1 plus x squared and then what we've got here is just really the same as rho times y prime is equal to rho, which is going to be x squared plus 1 to the negative 1/2 times x divided by 1 plus x squared. So somehow, at some point, I guess up here, I started accidentally writing it x squared plus 1 instead of its original form of 1 plus x squared. But that's alright, they're the same thing, so no big changes have happened here. But now let's think about simplifying this. So we've got here is x squared plus 1, or 1 plus x squared, however we want to write it. This is basically a power of negative 1. This is a power of negative 1/2. And so when we put them together, it's going to be a power of negative 3/2. And so that's going to give us the rho times y prime equal to x squared plus 1 to the negative 3/2 x, which now we want to anti-differentiate in order to get rid of this derivative. And so we're going to have rho times y is equal to, and over here we're going to have the antiderivative x squared plus 1 negative 3/2 times x dx, and then there's going to be a plus c at some point here. I'll wait to put the plus c until after I've actually executed the antiderivative. Now here we're going to again have an occasion for a substitution, and in fact the same substitution that we had before, of a u equals x squared plus 1, which then makes a du of 2x dx, and then that's going to lead to the more useful fact that just x dx is equal to 1/2 du, which means that the integral that we're talking about here, rho y, is equal to the integral, and now what we've got is u to the negative 3/2 times 1/2 du, which then is going to lead us to a power rule. So you add 1 to the exponent here, so that would make a negative 3/2 into a negative 1/2, and then you multiply by the reciprocal of that. We pull the 1/2 out to the very front, and times negative 2 over 1 u to the negative 1/2 plus c. Or actually, I guess really plus c right there. And then those cancel a little bit, and we remember what the u actually is, and so we're going to have a negative, and then here this is x squared plus 1 to the negative 1/2 plus c. And that's what rho y is equal to. But again, rho here was equal to, basically this. So then what that means is that x squared plus 1 to the negative 1/2 times y is equal to negative x squared plus 1 to the negative 1/2 plus c. And I'll just multiply both sides by the reciprocal of this, which would be this to the positive 1/2. And what we would then get, so basically divide both sides by this, and then what we would get is that y is equal to negative 1 plus x squared plus 1 to the 1/2 times c. Or I was talking to c here. So that is our so this is our family of solutions to this particular equation. And if you wanted to check this particular family of equation, this family of solutions, all you would have to do is take the derivative of it and then confirm that if you were to multiply it by 1 plus x squared, and then you were to subtract this times x, and then you were to just set it equal to x, then everything would cancel out and left would equal right. And what we did here was we multiplied by x squared plus 1 to the 1/2. Okay, so there's that. Now these families of differential equations still have constants in them, and the way to find a specific value of the constant for them is to use the initial condition if one is given to you. So initial value problems. So in these cases, these are the so there is also an initial condition given. Use it to solve for C. So an example of something like this might be if you were to take an expression like so. Let's take x squared plus 1 y prime plus 2x cubed y is equal to 4 e to the negative x squared and an initial condition of y naught equals 1. All right, well, first things first, what we've got in our current form is not a legitimate linear differential equation. So what we'll have to do is bring it up to code by dividing by x squared plus 1. Oops. Y prime plus 2x cubed over x squared plus 1 y is equal to 4e to the negative x squared divided by x squared plus, sorry, there was a typo in this from the very beginning, so it's 4x. Well, we almost got ourselves in over our heads on that one, so luckily we caught that before it was too late. It's 4x. Otherwise we were going to perhaps be in trouble. Okay, so now let's take a look at this and see what we can do. So here, the p that we need in order to find the integrating factor is going to be 2x cubed over x squared plus 1. Now this is a case of a function that when we are going to have to take the integral, we're going to have to be a little bit careful here. So that means rho is going to be exp integral 2x cubed over x squared plus 1 dx. And so when we want to take the integral of a function like this, one way we can do it is by rewriting it in the form that we would get by applying polynomial long division, for example. That'll be the easiest way to go about this. Otherwise, some other form of clever trickery might be necessary here. But here we're going to rewrite we're going to rewrite 2x cubed over x squared plus 1 using polynomial long division. So 2x cubed x squared plus 1. So first off, here you ask yourself, what do I have to multiply an x squared by in order to make a 2x cubed? And the answer is 2x. That's going to make a 2x squared plus 2x, and that you subtract, 2x cubed plus 2x, and that you subtract just like with regular long division, numerical long division, and then when you subtract these, you're going to get a negative 2x. And so what that's going to leave you with here is that 2x cubed over x squared plus 1 is the same as just 2x minus 2x over x squared plus 1. And then what that means is that the integral, thus, the integral 2x cubed over x squared plus 1 dx is going to be the integral 2x minus the 2x over x squared plus 1 dx. But we can separate these two integrals out, and we'll have the integral of just 2x dx minus the integral 2x over x squared plus 1 dx. And this is going to equal just x squared. This one is going to equal well, let's get to it in a second, 2x over x squared plus 1 dx. And here the u can be the x squared plus 1. Du can equal then 2x dx. And so then what we're going to end up with here, so I should say remainder negative 2x. Okay, so then what we're going to end up with over here is equal to x squared minus, and now what we've got here is the integral of 1 over u du, which is in other words x squared minus I should say minus the natural log of x squared plus 1. Alright, well then what that's going to make for us on the original problem, the problem that we started with here, we now have an integrating factor of exp x squared minus the natural log x squared plus 1. But exp, remember, is just a shorthand for the exponential function e to the x. And so what this is going to give us is actually just going to be e to the x squared minus natural log x squared plus 1, which we can rewrite according to the properties of exponents as e to the x squared divided by e to the natural log x squared plus 1 which is going to be just e to the x squared, and these are going to cancel each other out, and we're going to end up with just x squared plus 1. Okay, so that is the integrating factor that we are going to be multiplying all of the sides of the equation by, and then we're going to have to hope for the best. So remember where things stood prior to doing that polynomial long division in that integral. We had y prime plus 2x cubed over x squared plus 1 y is equal to 4x e to the negative x squared, all divided by x squared plus 1. And now we multiply by rho. So then we're going to have rho y prime plus rho prime y, taking a leap of faith here, hoping we did our integration properly, so that way what we have here times rho would be the same as just rho prime, and then that's equal to rho 4x e to the negative x squared over x squared plus 1. And so here what we're going to have is going to be just rho times y prime. Again, it's the product rule. That's the whole point of an integrating factor. And then over here, what's this going to be? So rho is equal to e to the x squared divided by x squared plus 1. And so what we're going to have here is going to be multiplied by 4x e to the negative x squared over x squared plus 1. And what we have here and here are going to cancel each other, which is always a very lucky turn of events. And what we're going to have is going to be 4x over x squared plus 1 squared And that's the same as the derivative of rho times y, so we anti-differentiate to get to the rho times y itself. And it's going to be the antiderivative 4x over x squared plus 1 squared dx. And once again, we've got a u substitution, and once again, it's the same old u. U is equal to x squared plus 1. Du is going to then equal 2x dx, which means that, for the record, 4x dx is going to be the same as 2 du. So then that means that rho times y is going to be the integral 2u over u squared. So in other words, times u to the negative 2 du. I should say just 2 u to the negative u du. And let's take that from the top. Take that from the top. Rho y is equal to the integral u to the negative 2 times 2 du. There. That's what I meant to say. There it is. And now we can anti-differentiate this using the power rule, add 1 to the exponent and multiply by the reciprocal of that. So the exponent is going to become a u to the negative 1, and then the reciprocal of that is just going to be negative 1 as well, times 2. Now we got a plus c finally. And so this is going to equal negative 2, and then the u here is going to be x squared plus 1. And this rho y. But now I guess it's a good time to remind ourselves what the rho was. It was e to the x squared over x squared plus 1 times y. And so we'll multiply both sides by the reciprocal of this. Negative 2 x squared plus 1 plus c. And when those multiply, they're going to cancel, but it's also going to distribute over here. And so we're going to end up with negative 2e to the negative x squared plus c times x squared plus 1 times e to the negative x squared. Now, once again, this was not just, though, a regular differential equation. This one happened to be specifically an initial value problem. So remember the initial condition, which was that y of 0 equaled 1. So plug in a 0 for the x, and we should be getting a 1. So, okay, what that means is then 1 is equal to negative 2 times e to the 0 plus mystery c times 0 plus 1 times e to the 0. So all the e to the 0s are just going to equal 1. And so what we have here is that, give me a second to get it all written down. So what we have here is that 1 is equal to negative 2 plus c, which by my calculations gives us c is equal to 3. Which then gives us a final solution to the differential equation of y is equal to negative 2 e to the negative x squared plus 3 times x squared plus 1 times e to the negative x squared. So there's the solution there. So that obviously was an involved process, and sometimes it is that way. Now, sometimes not only is it an involved process, but it's actually an impossible process. So note, when the integrations cannot be done analytically, we can write integral function solutions using the second fundamental theorem of calculus. And in particular, then, for example, we might have rho is equal to exp in the integral from x naught to x of p of t dt. Remember, this is a case where you have to change the variables because you can't use the same variable for your bounds of integration and for the interior of your integral. And then the initial value problem. So the initial value problem solution would look like y is equal to 1 over rho times y naught plus the integral x naught to x of rho of t times q of t dt but this is something we're not going to use this very often. So we won't do this very often, by which I mean hardly ever. However, in real life, integrals that are actually possible to find analytically are rather thin on the ground, and the most common case is actually integrals that can't be done analytically and have to be done by some sort of an approximate means, such as by use of an integral function. But we won't worry about that so much right now. Now here is the most important application of this for this section as far as we're concerned. So an application. And this is what's called mixture problems or mixing problems. And the setup here is that we have a vat or a tank of some kind, and we're tracking. So we track the concentration of a solution of a chemical solution. I don't mean a solution like what we were just saying, solution to a differential equation, but like an actual solution, something where some kind of solute is all dissolved. Of a chemical solution as a function of time. So here's the typical arrangement. We have a tank. We have a flow in, and we have a flow out. And an example of the sort of thing we might have here would be something like this. So as an example, an 800-liter tank with 400 liters of water and 50 kilograms of salt and let's say that this is dissolved into it initially. And then what happens is we have brine flows into the tank at a concentration of 0.25 kilograms of salt per liter of water at a rate of 16 liters per minute. And this new brine is mixed continually in with the old. Meanwhile, the tank drains at a rate of 12 liters per minute. So notice that it is flowing in faster than it is flowing out. So that means the tank, which is initially half full, will be getting fuller and fuller and fuller. And the question is, when full, what will the concentration be? So it's gradually filling up, and we just want to figure out when it is full, what will its concentration be? All right, so this is an example of a mixture problem. We have brine coming in, we have a tank, we have brine flowing out. So here now is going to be our approach. Give me a second to write that all down. So here's the approach to this and all mixing problems. The approach that we'll use to all mixing problems, or mixture problems. They go by both names. Alright, so we're going to break everything down into inflow and outflow. So the inflow, we have the RI, which is rate in. And this is in liters per second, so this is volume. Then we have concentration of the solution going in. Concentration of inflow. And so, actually, I guess in our example here, this is liters per minute. Then the concentration of the inflow is going to be in this case, kilograms per liter. And then the outflow is going to be the R out and the C out. Rate out, concentration out. Then basically the overall setup here, so X is going to stand, this is going to stand for the amount of the solute. And that's going to be, in this case, in kilograms. Then this is a function of T. Then concentration out is going to then be X divided by V of T, where V of T is the current volume. So not the overall capacity, just the volume at a specific time. And this is also a function of T, so we might specify that here. Then, in general, dx dt is going to be rate of solute coming in, and that's in other words going to be kilograms per minute, minus rate of solute going out, and that again is going to be in kilograms per minute. And that then would be the rate in times the concentration in minus rate out times the concentration out. But here that's going to be rate in concentration in minus rate out times X over V. And now here, let's then unpack the last piece of this that we haven't really dealt with. V is going to equal whatever the initial amount is plus how much faster the tank is flowing for how long it's been flowing. So it's going to be rate in minus rate out times time. Okay, so that gives us finally dx dt is equal to Ri Ci, in this case both of these are constants, minus R out, also a constant in this case, times x, which is not a constant, divided by the volume, which is going to be V naught plus Ri minus R out times T. All right, now to turn this into the default format of a linear differential equation, and it is linear in x, which is the important thing. X here is playing the role basically of what y was in the original framework. So this is linear. And it's linear in that it's going to look like dx dt. And now we move the x term to the other side, r naught over v naught, sorry, not r naught, r out, v out plus r in minus r out times t, and that all times x. And that's going to equal just the constant Ri Ci. So then P is going to equal R out, V out, Ri minus R out times T. Okay. So then here, so back in our example, the pieces of information that we were told the overall capacity was 800 liters, we had nothing to do there. We know the initial volume is 400 liters. We know that the initial amount was 50 kilograms. We know that the brine flows in at 25 kilograms per liter. So that's going to be the concentration in is equal to 0.25. The rate in is going to be 16 liters per minute, and the rate out is going to equal 12. So those are all the pieces that we have been given in the problem as stated, and now we just have to put the pieces into play. So dx dt plus R out, which is 12 over 400 plus, that minus that is 4t times x is equal to rate in 16 times concentration of the water coming in, which is 0.25. And now if I want, I can do a little bit of cleanup here. I've got a common factor of 4 here that I can use for a little bit of cosmetic arrangement here. Oops, keep doing that. Don't do that. It's not equals, it's plus. And then I'll divide everything by 4, so that'll give me 3 over 100 plus t x equals 4. And now then, what that means is that p is equal to 3 over 100 plus t, which means that rho is gonna equal e to the power of the integral of 3 over 100 plus t dt, which is then going to be equal to, here what we've got is a very basic u substitution, so basic that we don't even need to really worry about doing it as a u substitution. It's going to be 3 times the ln of 100 plus t. And I'm not going to worry about the absolute values right now, because we are talking about the time really only marching forward, not backward, so I'm not so worried about it. So t positive means no absolute value. Okay, so then we've got this, but once again we have a combination of an exponential function and a logarithmic function, so it should not surprise anybody that I have hopes of being able to apply some sort of property to clean that up, and sure enough, it's going to be the same property as what we did before. And so that's going to give us a rho altogether of 100 plus t to the power of 3. Okay, now back then to the actual equation. What we're going to have then is rho times x prime plus rho prime x equals rho times 4. And now we're going to start filtering in as convenient anyway, which the expression for rho wherever we can. And so we're going to have rho times x all prime, so that's me consolidating the left in the form of the product rule, times 4 times 4 times 100 plus t cubed. So then rho times x is going to be the antiderivative of 4 times 100 plus t cubed dt. T is now the function, or now the variable with respect to which everything is happening. And once again, this is going to be a u substitution with a nice u of 100 plus t, and so that's going to give us just 4 times 1/4 100 plus t to the 4th plus c. So that's me just adding 1 to this power, dividing by that, etc. And so then that's going to cancel, and we're just going to end up with 100 plus t to the 4th power plus c. But over here, this is what rho times x looked like, but what was rho? 100 plus t cubed times x. And so if I divide both sides by the 100 plus t cubed, then I'll just get an x on the left, and on the right, what I'll have, if I distribute here, is just going to be 100 plus t plus c times 100 plus t to the negative third. And now to find the value of c, we just have to use the initial condition, and the initial condition here was the initial value of x. X of 0 was in this case equal to 50. And so what we're going to end up with is 50 is equal to 100 plus 0 plus c to the 100 plus 0 to the negative third. So subtracting negative 50 is equal to c divided by, or times 10 to the, so this is 10 to the 2 time to the power of negative 3, so it's going to be 10 to the negative 6. And so that means c is going to equal negative 5 times 10 to the 1 divided by 10 to the negative 6, which is going to equal negative 5 times 10 to the 7th. Okay, so then that's going to give us our x, which equals 100 plus t minus 5 times 10 to the 7th, 10 to the 7th times 100 plus t to the negative third. And now, if we want to figure out what the volume of the tank is going to be once the tank is full, so tank is full when V equals 800, which means, in other words, that 800 is going to equal, what was the initial one? It was 400 plus 4 times t. So then that means that what we're going to have here is 800 equals 4. That's not accomplishing anything. Sorry, it's been an hour. It's getting a little worn out here. So we subtract the 400 from both sides, divide by 4, and we get t equals 100 minutes. So then, according to this, the x at t equals 100 so x of 100 would equal 100 plus 100 minus 5 times 10 to the 7th times 200 to the negative third, which will equal, according to the power of a mighty TI-89, will equal 100 plus 100 minus 5 times 10 to the 7th times 200 to the negative third will equal 775 over 4, or in other words, if I want the decimal here, 193 divided by 0.75. And these are kilograms. And then to get the final concentration when it is full, which was what the original question asked. So then the concentration so C of 100 divided by the 800 liters that the tank can hold is going to be approximately equal to 0.242. 0.242 kilograms per liter. Okay. So there's that. Notice that that's a number that makes sense because it's pretty close to what the concentration of the inflow was. And since we're talking about a relatively long period of time, what that means is that the overall concentration is more or less going to end up leveling off at the concentration of what the inflow was. And the concentration to begin with was 50 kilograms divided by 400 liters, which was 0.125, which was less than the inflow. So that means that the overall concentration is always going to be a little bit less than 0.25, but it's going to be growing and growing and growing to approach it. All right, well, that is quite enough for now. Join me next time for the next episode of Math 256. Till then.